Okay, so now once we have our geometries, really what we will want to start to understand is whether or not our molecules are polar or not. Okay, so this is one kind of application of our geometry, right? So to start, if we have just diatomic molecules, if we have different elements, then we're going to have a polar molecule, okay? It may not be very polar, it may be kind of just a little polar, but it's going to be a polar molecule, okay? Molecule, there we go. And this really comes from the electronegativities. Obviously, if there's an electronegativity difference, then one of the atoms is pulling more of the electrons than the other, which means that more of the negative charges are over on one side of the element than the other, okay, which results then in a polar molecule. With our polyatomic molecules, it gets a little bit more complicated, okay? So first off, we're going to ask if it is a polar bond. If it is a polar bond, then we're going to say, okay, maybe it is a polar molecule. That is where then we need to start looking at symmetry, okay? So this is where we look for the mirror test or just look for symmetry, okay? Okay, so an example, right, BeF2, we see that beryllium, fluorine's on either side, it's totally linear, which means that it's going to be symmetric. So this is a polar bond, but it is not a polar molecule, okay? If then we look at H2O, if we normally just write it like this, we may not see that actually this is not symmetric, okay? So if we go back and we look at our AX identifier, right, H2O is AX2 E2, right? This is a bent structure. So what that means is that we have kind of two hydrogens that are down one way, and then our oxygens are kind of on the front and the back. Or our electrons on our oxygen are on the front and the back. So overall then, we've got more electron density that is up above on the oxygen side, and less electron density that's on the hydrogen side. So we can draw a dipole like this, where our positive end of the dipole is pointing towards the negative end, where we have more electron density, and we do have a polar molecule. Okay? So another example with this would be like CH4. If we look at just CH4, we look and we see that the difference in electronegativities between carbon and hydrogen, it's pretty small. So it's small enough that we would say not a polar bond. So it's not going to be a polar bond, so we're not going to have a polar molecule. Okay? All right, so last two pieces here. Hybridization, what we're looking at is actually those bonds that we have with other, between atoms. So if we look at our CH4, right, we said that is a tetrahedral molecule. So electrons are normally in s orbitals or they're in p orbitals, but this doesn't allow for really good overlap of the electron density, right? We want to share that electron density so that the nucleus of one atom can share, be close to the electron density of the other atom, okay? So what the electrons actually do is they hybridize their orbitals, okay? And this may be complicated, but it sounds complicated, but it's actually pretty easy at this level, okay? So what we are going to talk about is mixing of the x or of the s and the p orbitals. Okay, and all we have to do is we got to count the number of things that are taking up space, and that tells us actually the hybridization of the central atom. So if we have the X plus the E from our ax structure is equal to just two pieces, right? Like AX2E0, then our hybridized orbital is just sp. If we have X plus E equal to 3 pieces, then we have sp2, and if it is equal to 4 pieces, then our central atom is sp3 hybridized. Okay? That's all that we need to know. The last piece with it, though, is we want to look at sigma and pi bonds. So when the atoms bond together, they do this hybridization where the electrons start to share, and we are able to have overlap between the electrons being close enough to the other nucleus, right? And so really when it hybridizes and we have that overlap of the electrons, we start to see these sigma and pi bonds. So a single bond, right, it's not a p orbital in general. It's going to be an sp or an sp2 or an sp3 orbital, and it's going to kind of point towards, right, from one nucleus pointed towards the nucleus of the other, so that more of the electrons can interact with the nucleus and our nuclei can be further apart. So a single bond, right, is a sigma bond. If we have a double bond, we have this same sort of overlap where our nuclei are kind of far apart. We have electrons that are kind of more likely to be closer to that other nucleus. But then we also have this p bond that starts to share over as well. So our double bond, we have a sigma bond, and we have a pi bond. Okay? And then a triple bond, we again have this sigma pointed towards the other nucleus, but then we also have the sharing of the p above and the p's kind of coming in and out of the plane. And so we have 2 pi bonds. Okay? So that's all the notes that we need to do for this unit.